download the first chapter of Eennlb's book off of our webpage.
Or, I'm sorry, I think you turned the mic off again.
It's on.
No, there should be the two.
That's off. That's on. I see that it's in the. That's on. This is mute. On.
Yeah, the headpiece.
Yeah. You want to try again?
There you go. Okay.
Yeah, the button is on. It's just the headpiece fell. Okay. Let me take my sunglasses off that way. It sticks. Okay, so first announcement is you got to download the first chapter of the book off of our webpage. Is it somewhere obvious? In the handout section of our webpage. So that's the first chapter. We're going to remove it at the end of the day, just so that we don't get into issues. There's a homework due. It's a written assignment next week, next Friday. And let's see, Wednesday is February 1, 2, 3. So that'll be February 3. And it's from chapter 1 of Eennlb, 128, 130, 133, 134, and 135. Just a little bit of warning, this assignment is pretty long. It's probably the longest or perhaps the time-consuming homework you'll have this semester, I think. The lab assignments are probably shorter than this, so don't leave it to Thursday night. And Cindy has office hours Tuesdays and Thursdays, and so get going on it a little bit earlier than you would otherwise. Then, just so that you know, the next assignment is going to be on tomography. And we got started a little bit late, simply because, although not compared to the last time I taught the course, simply because the book wasn't available at the beginning of the semester. So let me begin by asking if there's any questions or comments. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. Okay, what I'm going to let me number my pages so that we're all numbered. What we're going to talk about in today's class is reconstruction of signals in general, but most specifically images from partial information, in particular partial Fourier information. So last time's lecture was a special case of that. We talked about reconstructions of signals from their projections. You get projection in time domain, and you use that in order to you get the projection in the space domain, and you use that to reconstruct the entire image. And today, what we're going to talk about is two classes of reconstructions. One of them is reconstruction of signals, of discrete time signals, two-dimensional in particular, from their Fourier transform magnitude. And then we also talk about reconstructions of signals from their Fourier transform phase. And then we wrap up by talking about reconstructions of signals or images from their level crossings, in particular just zero crossing, and then move on to reconstruction signals or images from multiple level crossings, which happens to be my PhD thesis many years ago. So I'll start with some motivation. Why do we care about why do we care about the problem of reconstruction from Fourier transform magnitude? If you can zoom in here. Well, it has a lot of. I'll define exactly what I mean by magnitude and get mathematical in just a second. But for now, you can think of it as I have some signal x of n, and its discrete time Fourier transform is x of omega. It's summation of x of n times e to the minus j omega n. And suppose that x of omega is a function of continuous variable omega, right, in the frequency domain. And suppose I knew x of omega, magnitude of it, everywhere, or a lot of places, not just at n points, if I'm having an n-point signal, but suppose I knew x of omega at 2n, 3n, 5n, at arbitrary number of points. And the question is, knowing the magnitude only of Fourier transform, can I get back the original signal? That's what the problem of reconstruction from Fourier transform magnitude means. And I'll write these things down when we get to the analysis part, so it becomes a little bit more clear. But just so that you know what the applications are. There's great many applications where it's easy to capture Fourier transform magnitude by computing phase or capturing phase or measuring phase is very difficult, especially at very high frequencies, like at optical frequencies. So this problem has applications in like electron microscopy, crystallography, optical astronomy. And as I said, the motivation is that in a great deal of applications, you just don't have a phase information at very high frequencies. And sort of a bit of a history of who did what in this field. What I'm going to show in just 2 minutes or 5 minutes is that if you have an n-point finite support, one-dimensional discrete time signal, you can show that there's 2 to the n sequences that have the same Fourier transform magnitude as that signal. So even if you had the Fourier transform magnitude of that one-dimensional signal, from that you couldn't uniquely recover that signal. There's an ambiguity factor of 2 to the n. I'll show that in just a second. And people had known that for many years, 30, 40, 50 years. But what Monty Hayes in 1982 showed was that you could reconstruct multidimensional signals just from their Fourier transform magnitude. Okay, so theoretically, if you knew the magnitude, you could be able to, up to a factor of 2, ambiguity factor of 2, reconstruct the signal. And I'll show that result in just a second as well, mathematically. And there's a bunch of algorithms that people have proposed. One of them is the error reduction algorithm by Gertzberg and Saxton, hybrid input algorithm by Fenep at Eennlb, who at the time was at Eennlb, and also a non-additive algorithm by Davis Relevitz that appeared in 1988. However, even though mathematically Hayes showed that you can do unique reconstruction, from a practical point of view, all of these techniques and non-iterative techniques could only be applied to small signals. That means signals with a small region of support. I don't know, 10 by 10, 20 by 20, but not 512 by 512. And furthermore, the iterative algorithms generally stagnate. So in general, this problem of reconstruction from Fourier transform magnitude, even though theoretically it's been shown to have a unique answer, or almost a unique answer, factor of 2 ambiguity, in practice, this is supposed to be an ill-conditioned problem for large sequences. And I'll spend a bunch of either today's lecture or Wednesday's lecture to explain to you what ill-conditioned means. There's a notion of ill-conditioned problems, and then there's a notion of ill-conditioned algorithms. How many of you have heard of this word? 1, 2. Okay. And what that means is that if you perturb the Fourier transform magnitude just a little bit, that results in a very large change in the recovered discrete time sequence. That's kind of what ill-conditionedness means. And so you might say, well, where do these perturbations come from? What are you talking about? Well, perturbations come in as soon as you enter your data into the computer, because the computer doesn't have infinite precision, plus your arithmetic operations inside the computer doesn't have infinite precision. So every time you add 2 numbers, be it in floating point or fixed point or whatever, there's a little bit of round-off error introduced, and that's the perturbation. And it's those perturbations that make the problem be ill-conditioned, and that would mean that the Fourier transform magnitude has to be specified with a great deal of precision, and you have to have a great deal of precision in your computation in order to get answers. In general, what's another example of a problem that's very ill-conditioned in real life? Forget about signal processing, all of that. We almost deal with it on a daily basis. You watch the news, like if you're up at between 6 and 7 a.m. and watch the news, you hear about it like 100 times on all the channels. The weather, right? You can't predict the weather accurately more than 5 or 6 days ahead, simply because it's an air-conditioned problem. You need to know the initial conditions of the current pressure, temperature, etc., to infinite precision if you want to apply mathematical modeling and predict it for many days ahead. That's why we can't tell you what the weather will be like exactly a year from now today, simply because it's an ill-conditioned problem, and you need to have very, very precise input, extremely precise calculations, infinite precision. So that's another example of an ill-conditioned problem. I'll talk about ill-conditioned problems and algorithms in today's lecture. I'll just wrap up by saying that in 1990 I did some work where I showed that if you have the Fourier transform magnitude of a signal, and as well as that if you just one bit of space domain information, just cross a signal in the time domain or space domain with a threshold, and just tell me which pixels are above and which pixels are below. Those two together, knowledge of those two, can make the problem well conditioned and can result in successful reconstruction of signals. So let me now try to more formally introduce this problem, and instead of waving my hands. What we're going to talk about today in general is reconstruction of 2D signals from partial Fourier information. And again, why Fourier? Because in great many physical applications, a Fourier transform of a signal is what you capture, is what you automatically get from your measurement system or from your data acquisition system. Fourier transform occurs in many applications in nature. Okay, so the motivation is really that there's lots of applications like electron microscopy and astronomy, crystallography, etc., optical astronomy, crystallography. Okay, and we're going to consider three distinct problems in this space. One of them is from Fourier transform magnitude, FTM, magnitude of the Fourier transform. The other one is phase reconstruction from phase of the Fourier transform. And the third one is reconstruction from level crossings of a signal in the space domain. Okay. So let me begin from Fourier transform magnitude case and talk about reconstructing signals from one-dimensional signals from their Fourier transform magnitude. Can you roll up just a little bit, please? Thank you. So recon from Fourier transform magnitude. And we're going to consider the one-dimensional case. So what we want to consider is a signal, a discrete time signal. This is x of n, discrete time. That means this n takes on integer values. It's a one-dimensional signal. It has n plus 1 non-zero points. And it's non-zero specifically for indices 0 all the way to n. Okay. And what do I mean by reconstruction from Fourier transform magnitude? Well, what I mean is we know the discrete time Fourier transform of x of n, which is x of omega, which is this summation n equals 0 to n of x of n e to the minus j omega n. And this is Fourier transform magnitude. And what I mean by reconstruction from Fourier transform magnitude is that we know the magnitude of x of omega. We know this guy. Okay. And remember, this omega guy is a continuous variable. So if I were to plot a magnitude of x of omega for some signal, It will look like that. This is the guy that's periodic with period 2 pi, and it repeats itself here and here. But it's as a function of omega. This omega is a continuous variable. This is not a discrete. Um, this is not a discrete signal or function. This is a function of a continuous variable. Okay. So the question that we want to ask is, if we know x of omega, can we get x of n back? Okay. So the first thing that you're going to start asking me is that, well, in real life, even though x of omega is a function of a continuous variable omega, in real life, we don't know it at infinitely many samples of omega. We only know it at finitely many, right? At the end of the day, when Bernard Boser puts his A to Ds in, I don't know, X-ray detectors or various systems, he samples at discrete locations. He can't put infinite number of A to Ds there, or else his budget will go through the roof, and nothing will work properly. So the first question I ask you, and I think the answer to this is pretty obvious, if I sample this x of omega, a magnitude of x of omega, at n plus 1 points, suppose I knew the sample is at n plus 1 points, can I then uniquely recover x of n? I'm saying magnitude of x of omega, not x of omega. Generally speaking, if you look at this equation, if I knew samples of x of omega at n plus 1 points, this is a one-dimensional polynomial in x of n, and I can just find the coefficients of that polynomial, solve a linear system of equations, and find x of n, right? Is that clear by just looking at this for everyone? But that's not what I said. I asked if I know the magnitude of these guys. Suppose instead of knowing x of omega itself at n plus 1 points, which would have enabled me to solve a linear system of equations to get x of n back, suppose I gave you the magnitude of it. Can I then get back x of n? I see some no's. Okay, that's correct. And why? It's very simple, because the phase can be anything, because I can assign some phase and solve a linear system equations, get one value for x of n, and then I can assign another phase values to those n plus 1 samples and get another x of n. And as many phases of x of omega I can cook up for those n plus 1 samples of x of omega, I can reconstruct x of n that many different ways. Is that clear, everyone? First of all, does everybody know about linear system of equations and stuff like that, right? So when I say I know x of omega at n plus 1 points, and x of n is related in a linear system of equations, if somebody doesn't know it, let me explain it now so that we don't get into trouble like towards the end of the lecture. Is that clear, or shall I quickly give a... yeah. I mean, basically what's happening is you have a matrix equation of x of 0 all the way to x of n, and here this is equal to x of omega 1, x of omega 2, or 0, x of omega 1, all the way to x of omega n plus 1. All I'm saying, and then there's a matrix here, which would be e to the minus j omega 0 times x of 0 times 0 times, and then e to the minus j1 times omega 1 times x of 1, e to the minus j2 times omega 2 all the way, and then the next row, sorry, these are all omega 0, and then the next row is e to the minus 0 times j times omega 1, e to the minus j1 times omega 1, e to the minus j2 times omega 1, all the way, e to the minus j2 times omega n. This is n. And the last row would be e to the minus 0 times j omega n, e to the minus, sorry, this is omega 1 again. God, I make so many mistakes. E to the minus j 1 times omega n, e to the minus j2 times omega n, e to the minus j n times omega n. So is everybody clear about this? So I multiply this row by this column, I get this. So suppose that suppose I had n plus 1 samples of x of omega. I knew it at x of omega naught, I knew it at omega 1, all the way all to omega n. Then using this, I can just expand this equation for different values of omega naught. So for different values of omega. So this row corresponds to omega naught. This row corresponds to omega 1. This row corresponds to omega n. But this times that, plus this times that, plus this times that, da da da, plus this times that equals this. So this is a matrix. This matrix times this vector equals this vector. This is a linear system of equations. It's called linear because our unknowns, in this case x of 0, x of 1, are entering the equations in a linear fashion. There's no squared, there's no x of 0 squared, there's no cross terms, there's nothing like x of 0 times x of 1. There's no square root of x of 0, there's no 1 over x of 0. I mean, we all know what linear means, right? The linear system of equations, matrix times vector equals vector. And can we solve that or not? What do we know about solving linear system of equations from linear algebra? We can solve this if its inverse exists, or other words, if its determinant is non-zero. And can we say something about determinant of this matrix? This is a van der Waals matrix, and van der Waals matrix is a special kind of matrix where you have, if you think of e to the j, for example, omega naught as variable, I don't know, p. So this is p to the 0, p to the 1, p to the 2, all the way p to the n. And think of this guy, e to the j omega 1 as q. So you have q to the 0, q to the 1, q to the 2, all the way q to the n. So this matrix has a special structure because it's of this form of each row being something to the power of 0, something to the power of 1, something to the power of 2, etc. That's called the van der Waals matrix. And van der Waals matrices have non-zero determinants, provided p is not equal to q, provided that in other words, provided these omegas are distinct from each other. Right? And we knew that already. I mean, where else have you seen a matrix like that? When you do DFTs, right? When I'm computing DFT, I'm just taking equally spaced samples of x of omega. And of course, we know the DFT matrix is definitely non-singular. You might have thought, well, it's non-singular because I'm taking equally spaced samples of x of omega. But the answer is it need not be. And in fact, what other reason do we have to believe that this is a non-zero determinant matrix? Because we already went over this in the first lecture, or I forgot the second lecture, which is this is a polynomial, right? These are the coefficients of the polynomial. If I let e to the j omega be x, okay, then this thing can be written as summation from n equals 0 to n of, oh, I already have x. Jesus, let's call it y. X of n times y to, let's call it y to the n. So this is a polynomial in y. And we already know that if you have a one-dimensional polynomial, if you sample it at n arbitrary points, you can uniquely recover the coefficients of that polynomial. Why? Because of the fundamental theorem of algebra, because you can factor it into simple terms, and because you can write the van der Waals matrix. I mean, all of these things are related to each other, right? So we already know that sampling a one-dimensional polynomial at arbitrary points, polynomial of degree n, at n arbitrary points, results in unique reconstruction of the polynomial. And we know that because you can form this van der Waals matrix, and you know van der Waals matrices have non-zero determinants, all those things. Is that clear to everyone? Yeah. Okay, so now coming back here, so how do we get distracted to that? Well, staring at this, if I sampled x of omega at n plus 1 points, I could easily solve this linear system of equations. This has a non-zero determinant, and find these coefficients, and I'm done. But my question was something different. I was asking, what if we know the magnitude of these guys? Only. And the answer is, well, if you know the magnitude, the phase for this, it's in order for me to recover x of 0, I would have to know the phase for this, the phase for all of these things in order to solve the linear system equation successfully and figure out what the x's are, right? And I can cook up any phase for this one, this one, this one, this one, this one, and depending on how I cook up and what I cook up, I get a different x signal, right? So indeed, if I sample this x of omega guy at n plus 1 points, the magnitude of it, I definitely can reconstruct the signal x of n, right? Because I have a linear system of equations, but I only know the magnitude at the right hand side, and the phase could be, you know, anything, ambiguity on the phase, right? So coming back here, so coming back here, let's write this down. So if I know magnitude of x of omega at n plus 1 points, I definitely cannot reconstruct the signal. In fact, ambiguity factor is infinity. I can there's infinitely many ways I can assign phase to each of these guys, and each one I get a different signal altogether. But the more interesting questions, and that's why we even bother talking about reconstruction from Fourier transform magnitude, is what if I oversample in the frequency domain? What if instead of sampling at the magnitude at just n plus 1 points, I sample it at 2n, 4n, 6n, 8n, 10n? I know the value at lots of samples. In that case, it's true I've lost the phase information for the Fourier transform, but I'm kind of trying to compensate for it by having more magnitude samples. So in the language of this linear system of equations, now I have a square matrix here, and n plus 1 unknowns and n plus 1 knowns. But what if I had just n plus 1 unknowns, but on the right hand side I'll make it to have 2n or 4n or 8n samples? So the picture then would look something like this. Would look, you know, a tall and skinny matrix times x of 0 all the way x of n equals a tall and skinny vector, which would be x of omega naught magnitude squared, magnitude of x of omega 1 squared, all the way x of omega n squared. And then here would be the usual rows. It would be e to the minus 0 times omega 0, e to the minus j 1 omega 0, da 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 da, e to the minus 0 j omega 1, e to the minus 0 j omega n, e to the minus j 1 omega n, da 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 da, etc. The same kind of matrix, but this would be tall and skinny. So let's say this would be 4n, and this would be 4n, and this is just n, or roughly n. So the fact that we've lost phase, but now we have more of these samples, can we reconstruct? Okay. And so question is, can we reconstruct? Can we uniquely reconstruct if we oversampled in the Fourier domain? And the answer here is that for one-dimensional signals, it doesn't even matter that you oversample. There continues to be an ambiguity factor of 2 to the n, and for multidimensional signals, you're okay. You could uniquely reconstruct. So that's what I'm going to show kind of the rest of the lecture. So the answer is, for 1D signals, no, 2 to the n ambiguity. And for MD signals, multidimensional signals, it's a yes. Even though in practice the algorithms have trouble converging and various other things. Okay, so let me, if you can roll back just a tiny bit so people can see. Great. So to show that, I'm going to introduce, so I'm going to start with the 1D case. I'm going to introduced the notion of autocorrelation function. And this discussion actually becomes a little bit technical and would require you knowing the properties of Z transforms and other things like the back of your hands. If you don't follow it, don't worry about it too much, but feel free to come and ask me questions at the end of the lecture. So I'm going to introduce this thing called autocorrelation function for a signal x of n. And you've probably seen it elsewhere. So suppose I have R of n and summation over L of x of L, x complex conjugate of L plus n. So R of n is called the autocorrelation function of x. And it has a Fourier transform. Okay, so R of omega, which is the discrete time Fourier transform of R of n, which is R of n e to the minus j omega n, has a Fourier transform that you can show is related to the Fourier transform of x in the following way. It's the Fourier transform magnitude of x squared. So what that means is that inverse Fourier transform of x of omega is just R of n. Okay? So if the question I'm trying to answer is, if I know magnitude of x of omega, can I get x back? Well, that's kind of, if I know magnitude of, and I'm assuming I know that arbitrarily large number of points. 2n, 4n, 6n, pick your choice. You know, you can have as many as you want it. Let's say we've asked Bernard Bozer to build a ton of these A to D sampler and things. So we can sample this guy at infinite, if we wanted to, as many numbers as we wanted. So the question really becomes, because x of omega squared is the Fourier transform of R of n, the question then becomes, if we know R of n, can we get x of n? Because knowing the Fourier transform x of omega squared is the same as knowing the signal itself. We already went over that. If you know the Fourier transform of any signal, not just its magnitude, but the whole thing, because this is the whole Fourier transform of R. So if we know this, we know R. So the question is, can we obtain x from R? Okay, and you can already see why I introduced its autocorrelation function, because of this lucky relationship. So now I'm going to take you to the Z domain and talk about the Z transform of R of n. So Z transform of R of n, which we denote by R of Z, you can show, because of the way we constructed R of n, is nothing but x of z times x complex conjugate of 1 over z complex conjugate. And by definition, it's summation of R of n z to the minus n. And this goes from n, little n going from minus capital N to plus capital N. Okay. So because of the way we constructed R of n, the extent or the region of support of R of n is from minus n to plus n. Okay. And now I'm going to introduce one more terminology, which is just a big sounding name terminology, but it's in fact very simple. We're going to talk about associated polynomial to R of z. So associated polynomial.
Just a quick question.
Yeah, sure.
The sum you wrote on the far right of that last equation, is that the definition of what the Z transform is?
Yeah, generally
I've never
speaking,
seen
this
it
goes
before.
from n minus infinity to plus infinity, but the reason I've limited it is because x of n has finite region of support, and because R of n is built from x of n in this manner, R of n also has limited support. So generally speaking, it would go from minus infinity to plus infinity, but in this case, because of the assumptions we made on the extent of x of n, and therefore extent of R of n, because of this relationship, this is what happens. So is that clear? Any other questions? Yeah, please.
For, let's say you get the magnitude of x omega, do you
Yeah.
need just n plus 1 sample to recover R of n, or you need more?
No, you need, because it has 2n plus 1 unknowns, so you need because R of n has 2n plus 1 samples, right? So you need theoretically, you need at least 2n plus 1 samples of x of omega in order to build R of n from it, right? Because of this argument that we just went through.
Okay, no problem.
All right. But again, in this discussion, we're assuming that we have plenty of samples. We can have n, 2n, 4n. You know, this Boser guy has given us all the 8 of these we ever wanted. So there's no short. We're not stingy on the samples. And that's why this result is kind of amazing. Is that even if you knew x of omega at infinitely many points, you still, you still couldn't figure out what x of n is. That's what the gist of this argument is. Okay, so we're talking about associated polynomial to R of z, and we define it. I put this little triangle for definition as p sub R of z, which is summation from n equals 0 to 2n of R of capital N minus little n z to the n. It's essentially this same polynomial up here. I'm just shifting everything so that instead of the powers of z ranging from minus capital N to plus capital N, now it ranges from 0 to 2 to the n. 0 to 2n, sorry. Okay. So it's really nothing fancy about it. And there's one observation I like to make about both about R of n is that R of n is a symmetric signal. We all know that if you start with a signal and you take its autocorrelation function, you get a symmetric function. So these coefficients are symmetric, just by the virtue of the fact that they're resulting from a correlation process. And now, invoking the properties of Z-transform, we can say that since the coefficients of this associated polynomial are symmetric, then we can have the following property, in that if Z0 is a 0 of PR, then so is Z0 complex conjugate minus 1. So since PR of Z, since coefficients of PR of Z are symmetric, we can conclude that if Z0 is a 0 of P sub R of Z, so is Z0 complex conjugate inverse. Which means that we can write, we can factor PR of Z in the following form. If you can roll up so half of the other page is shown. Great, thank you. So which means that we can factor PR of Z as follows. As some constant, let's just call it A product of a bunch of zeros, which we call Zi, but then because if Zi is a 0, this guy is also a 0, then you have another term here, which is 1 minus Zi complex conjugate Z, which is saying that Zi complex conjugate inverse is also a 0 of PR of Z. Okay? Pardon?
Is that Zi conjugate times Z?
Yeah, that's right. So what does all of these things mean? Well, what that means is, for example, let's just draw the. Well, let me do one more. Well, let me draw this. That's better. So suppose I have this as a unit circle. Then for example, if this guy has a 0 Z0, then it has also a 0 Z0 inverse complex conjugate. If it has a Z1, then it will have another one. If it has Z1 here, then it could have Z1 complex conjugate minus 1 out there. Okay? So the last thing I want to define is a definition of a mirror polynomial. Mirror of a polynomial, rather. Okay? So, and this is the last definition we need before we conclude this discussion. And it goes like this. Associated with any polynomial, there is a mirror polynomial that consisting of the coefficients of the same one, but in reverse order and conjugated. So, associated with any polynomial, there is a mirror polynomial consisting of coefficients in reverse order and conjugated. So if I have P of z, a polynomial that, for example, goes from n equals 0 to capital N, P sub n z to the n, then its mirror is given by P tilde of z as summation from n equals 0 to n. But now the coefficients are reverse ordered. That means it's P of capital N minus little n, and then complex conjugate z to the n. Okay. So why did I introduce this mirror polynomial idea? Well, because now we can write down more generally the following thing, in that if I have again, roll up so we can see the definition up here. So if I assume I have a signal y of n that has autocorrelation r of n, and at this point it's not quite clear if y of n is the same as the x of n we started off with or not, but then we can write down its associated polynomial Pr of z, which we introduced up here, right, as a product of a polynomial Py of z and the mirror of it, P tilde y of z. In other words, having defined what a mirror polynomial is in this kind of fashion, we can show that this associated polynomial for signal x that we came up with, which can be of this form, and we diligently defined it like this, etc., etc., it's just a product of the one polynomial times its mirror. So now the why there's 2 to the n possibilities becomes clear. If I come back to this picture and I've put the pole 0, I've put the zeros of this polynomial in this picture right here. So that's a z2 here, z2 complex conjugate minus inverse there. If I know r of n, the question was, if I know r of n, can I get back x? And from this picture and from these analysis, you can immediately see that we can't. Why? Because if I know r, then I know r of z. If I know r of z, then I can build Pr of z, which is the associated polynomial. Now that associated polynomial has this kind of factoring, right? And what we're saying here is that, so when you factor this thing, all you know is there's a bunch of zeros for this thing all over the place, right? But it's very hard to know. There's 2 to the n ways of associating for each of these zeros. Let's talk about z naught. You could have, let's see, there's 2 to the n ways to generate P of y, given that you know P of r. Okay? So if you have a signal, if you have a general signal y of n, and it has P of y and it has Py tilde, and all you know is Pr of z, which is this zero pattern that you see in this place, you don't really know to associate with the signal. You don't really know whether this Z naught is part of Y or is part of this, or whether Z naught inverse is part of this or part of that. So for every one of these zeros, and there's n of them, right? For every one of them, Z naught, either Z naught could be part of this or Z naught inverse can be part of that. So a tree branches in two. In either of these two conditions, either Z1 is part of this or Z1 complex conjugate inverse is part of this. Now we have four possibilities. Each of those four possibilities, then you look at Z2. Either Z2 is part of the signal or the complex conjugate inverse of it is part of the signal. That's now 8 possibility. So as I go through the zeros, I can, what we're trying to say is that given PR of Z, you can factor this thing 2 to the n possible ways. There's 2 to the n possible ways we can factor it, and therefore there's 2 to the n possible signals with 2 to the n combinations of zeros that could all have the same PR of Z, which means they could all have the same R of Z, which means they have the same R of N, which means that there's the ambiguity that's going on. Is that clear? So in other words, what I'm trying to say is that there's 2 to the n ways, depending upon whether you pick the zero to be inside, outside, each one of the zeros associated with PR of Z. At the end, when you look at PR of Z, all you see, you can factor it out, you see a bunch of zeros. And you can't really distinguish to see for the original signal whether these zeros happen to be for the original signals, but all the 2 to the n signals that could have Z naught or Z naught inverse complex conjugates with zeros, Z1 or Z1, all of them have the same PR of Z, and there's no way to know which of those 2 to the n signals were the original X of them we were after. Okay? So I guess the missing link that I might have explained is that these Z naught, Z1, etc., these are the zeros of the original signal, but we don't know, but it could be this one or it could be that. It could be this or it could be that. For every pair, it could be the original zero or it could be the one that's inverse and complex conjugate. So because of that, there's 2 to the n possible signals in time domain that will all have the same PR and therefore the same R, and that's what causes the ambiguity. So there's 2 to the n ways in order to generate Py of Z. In other words, Py of Z could be, let's say, square root of A, right? Because these two polynomials are the same, so it's square root of A, and then a product of Z minus Zi and a product of another Z minus Zj complex conjugate, but we don't really know what these indices are. I is in the little I is in some set I, and J is not in I, and this I can be any subset of all the way 1 through n. So for example, I could have, if n is 5, I could pick 4 zeros here and 1 there, or and it could be any one of the 4 zeros and any one of the ones. I could have 2 here, 2 there. It's just there's 2 to the n enumeration of possible factoring of this thing that would result in 2 to the n different signals. Okay? So at the end, this PR, which is the same as this PY, can be factored in this polynomial times its mirror, but figuring out which zeros go to the polynomial and which one goes to its mirror is difficult. And at the end, that's kind of what prevents us from knowing which one of those signals there are. Okay, is that more or less clear? Are there any? I see a lot of.
So you define this Z transform, and then it looks like this associated polynomial is just like a shifted version of that.
Right.
And so I guess I'm just confused. So the Z transform is related to the transforms of the original is the product of the transforms of the original function.
R of z?
Yeah, R of z is like the product of.
R of z is z transform of R.
Right.
Right? And it has it has a bunch of zeros, right? And specifically it has 2n zeros, right? And of that, n of them belong to x. The zeros of R of z come in pairs, right? For each pair, let me write it in this sheet. So R of z has these pairs of zeros: z0, z0 complex conjugate inverse, z1, z1 complex conjugate inverse, da 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 da, all the way z to the n complex conjugate inverse, right? These are all the zeros of R of z, or PR of z. It doesn't matter. They're all the same thing. And at the end of the day, x of n has n zeros, but each one of its zeros comes from each one of these pairs. Like its first zero or its zero can be this one or that one. Its second one can be this or that. Its nth one can be this or that. Okay? So to build x of n, if you start from R of n and you want to get x of n, there's an ambiguity as to the first one. Is it this or is it that? So I can build 2 to the n signals that will all have the same R of n. Is that clear? There's 2 to the n possibilities for x of n that result in the same R of n. Because of the structure that R of n has. Did that make it a little bit more easy to understand? Did it answer your question, Chris? Or still not yet? Okay. Question.
I have two questions. The
Mhm.
first is the autocorrelation of autocorrelation goes back to the original function.
I'm sorry, is the autocorrelation what?
Autocorrelation of the autocorrelation gives you the original function.
Autocorrelation of an autocorrelation give you the original function.
Right.
No, because
Okay.
every time I take an autocorrelation of signal, its extent becomes double. So
I'm
if I start with an n-point sequence, its autocorrelation has 2 endpoints roughly. And then if I take autocorrelation of that, I get 4 endpoints.
So I'm confused with the notation of a pyx. What is really pyx?
Pyx. We have py of z. Is that what you mean?
Right, py of z.
Yeah. I think the only reason I introduced the mirror polynomial is to say the following, is that this you know what PR of z was, right? The only reason I introduced this mirror business is to say that PR of z can be written as a polynomial and its mirror. And, right?
Right.
And given this structure for PR of z, there's going to be 2 to the n ways I can do this factorization. That's all there's 2 to the n possibilities for y, in other words.
So
Depending upon which zeros of r I pick to assign to y.
So did you assume that once you know py of z,
Mhm.
you can reconstruct
That's right.
x?
But I'm saying there's 2 to the n ways I can do this factorization.
So
Right.
second question was you mentioned there was an infinite number of possibilities when you have n plus 1 samples.
Yeah.
But here you only have two to the.
Here I'm assuming I know I have many samples. Remember, suppose that this 2 to the n ambiguity was not even there. Suppose God came and told you, oh, of this 2 to the n signal, that's the one. That's the one that corresponds to this, right? So then you can get R of n, right? But to go from R of n to X of n, well, I guess by that time you know what the answer is. See, the reason I said here, I'm assuming I only know n plus 1 samples of it, right? So if I want to solve the linear system of equations as I had before, I can assign an arbitrary phase here. I can assign phase 0, phase pi over 3, phase, I can assign different phases to this and then solve an solve a linear system of equations to find x, and I get a different answer. And this setup, on the other hand, I'm kind of assuming that I know x of omega at any point I want it to. There are two different, I can see why it causes confusion. There are two different setups. But you can see in this setup, if I pick one set of phase, I get one signal. I get another phase, another signal. It's a linear system of equation where on the right-hand side, instead of knowing the exact values, we only know the magnitude of what should be there. So you can assign arbitrary phase, and based on what arbitrary phase you assign, you can get a different signal. I think perhaps, yeah, this picture kind of sums it up in a nice way, is that these are the zero pairs of R of Z, and depending upon which one of these, in each stage, which one I pick for my signal, I can end up with 2 to the n signals. All of them have the same R of n. That kind of sums it up in a nice way. Question, yeah.
So when you're using the autocorrelation method, you basically rely on perfectly evaluating the autocorrelation function in time. So and you need the 2n plus 1 samples to do that, right?
Right.
Of the magnitude.
The question that was asked was, can I go from R of n from X of n? Can I go, if I manage, let's see. Yeah, this question here was, the question here was, if I know x of omega squared, in other words, R of omega, let's call this R of omega, this is R of omega, right? Oh, we've already defined it here. If I know R of omega, can I get R of n? That was the question that was asked, and the answer is, yeah, as long as you sample R of omega at 2n plus 1 points, you ought to be able to get R of n, yeah.
So that means that if you have more than 2n plus 1 samples of your magnitude of x of omega, it doesn't help you.
Right. The problem is not going from R of omega to R of n, or going from x of omega squared to R of n. If you know x of omega squared, you can uniquely reconstruct R of n. That's not the problem. The problem is that R of n correspond to 2 to the n possible x of x's. In other words, if I have a correlation function, it could correspond 2 to the n possible discrete time signals could have the same correlation function. That's the crux of the matter.
Yeah, so if I understand correctly, so if you have a number of samples of x of omega magnitude, so if you have n plus 1 samples, then ambiguity is infinity. And then it's infinity until you know 2n plus 1 samples, in which case it becomes 2 to the n.
Right.
But then after that, it's still 2 to the n.
Yeah, that's right. That's exactly right. You got it. That's exactly right. So here, that's right. The ambiguity is not going from R of omega to x to R of n, or going from here to R of n. That we can do with 2n plus 1 samples. But once we have R of n, there's 2 to the n possible signals that have the same correlation, autocorrelation function. That's the problem. Okay, so we're all convinced that the 1D doesn't work out, and we don't just pack up and go home. Now we're going to consider the two-dimensional case for Fourier transform magnitude. And what does that mean? Well, now we have omega 1, omega 2 that repeats itself periodically. It's doubly periodic. It goes from minus pi to pi. And now we're assuming that we know x of omega 1, omega 2 squared. And again, for simplicity, we're not going to be stingy with the number of samples. We're assuming we have, if our signal, if our x of n1 and n2, we assume is n by n, has the n by n region of support, okay? So we assume that we know x of omega 1 and omega 2 at more than n squared point, let's say 4n, 8n squared, whatever. And now we're asking, can we recover x of n? And what has changed in 2D is that, unlike one dimension, most two-dimensional polynomials are irreducible. That means they're not factorable, and I already talked about that a little bit in the first lecture. So in 2D, unlike in 1D, most 2D polynomials are what's called irreducible. Reducible means that they can be factored. Irreducible, IR at the beginning, means they can't be factored. That means they're non-factorable. In fact, again, Monty Hayes shows that, actually you came from Georgia Tech. Did you ever take courses from Monty?
No.
Okay, but you've heard of him. Right, good. In fact, Monty Hayes showed that if the class of irreducible polynomials is of measure 0 in the class of irreducible two-dimensional the class of reducible two-dimensional polynomials is of measure 0 in the class of all 2D polynomials. That means if you close your eye, throw the darts, and pick a random 2D polynomial, chances are 99.99999% that it is irreducible. That means it can't be factored. Simple language, most 2D polynomials just can't be factored. So, and he did his thesis, he used that fact to show, and I won't show the proof of it, but I mainly state the theorem that he came up with, and this is 1982 approximately, that says the following, that says, if x of n1 and n2 has irreducible associated polynomial, and we already know what associated polynomial means. It's just the z transform, but just shifted so that the powers of z are positive. Instead of going from minus n to plus n, they go from 0 to 2n or something like that, right? Associated polynomial. Then all other y of n which have the same Fourier transform magnitude are equivalent, and we're going to define what equivalent means, to x. And equivalent means the following. We say y of n1 and n2 is equivalent to x of n1 and n2 if any one of these three things happens. If y of n1 and n2 is equal to e to the j theta times x of n1 and n2. And you can already see why that's the case, because the Fourier transform magnitude of this guy and the Fourier transform magnitude x and y, if they're related in this manner, they're the same. So there's an ambiguity factor of e to the j theta, but we can come up with conditions to easily remove that. We'll see that in 1 second. Another possibility for equivalence is that y of n1 and n2 is actually let me cross that out. Just say I'm going to write it in one shot instead of multiple steps. Is x of k1 plus or minus n1 comma k2 plus or minus n2. That has everything in one shot rather than multiple shots. So let's make few observations on this. Observation 1 is that if x of n1 and n2 has magnitude x of omega 1 and omega 2, then we know that e to the j theta times x of n1 and n2 also has the same magnitude, right? Mathematically, it's very easy to show. So this e to the j theta factor, whatever phase factor instead of is in the space domain in front of the signal, is indistinguishable. But in a minute, we're going to constrain our signal to be real and positive, and that knocks out this e to the j theta. Observation 2, I'm just giving you intuitive reasons as to why we have these things here and these things here. If x of n1 and n2 corresponds to x of omega 1 and omega 2 magnitude squared, if its Fourier transform magnitude squared is this, then we already know that if it's shifted by k1 and k2 in the space domain, we get the same Fourier transform magnitude. We know that shift by k1 and k2 in space domain has the same Fourier transform magnitude. Okay. So So the shifting also causes a lot of problems. So how do we try to uniquely specify x? So in other words, let me just try to roll back, please, so I can see half of the other sheet.
I had a quick question.
Yeah, sure.
I don't know. In the past, whenever when you add a phase to some function and then transform it, you shift the frequencies that the transform is evaluated at.
If the phase shift is a linear function of the frequency, then it results in a shift. If the e to the j omega you put here is e to the j omega 1 times alpha, for example, then it corresponds to shift of alpha in this thing. I was going to say one more thing about this. Let me say that if the question still, yeah? Did I answer your question? Oh, actually, let me let you finish it. Go ahead.
Well, yeah,
If you say if it doesn't shift the I'm talking about observation 1 where you add the e to the j theta and then take the transform.
Yeah.
I've always thought that when you do that, you end up switching the frequencies that you evaluate the transform at.
Oh, but this e to the j there has no n function dependency. It's a constant.
okay.
It has no. It's like theta can be 0, then it's 1. Theta can be pi over 2. It's not an n1 or n2 dependent thing, right? It's just multiplying the signal by constant, right? So did that clear? Okay. So looking at this observation here, so if I shift by k1 and k2 in the space domain, I get the same Fourier transform magnitude. That means that if my original signal, for example, had this region of support as a function of n1 and n2, now if I just shift the thing in n1 and n2, then I get the same Fourier transform magnitude. So no wonder there's an ambiguity still hanging. And you might, with all these ambiguities, you might be getting very worried, but don't. We'll remove them. And then we have our observation 3, which is a rotation factor. And that's the one ambiguity we're going to have a hard time getting rid of, and that is if x of n1 and n2 has a Fourier transform magnitude this, then y of n1 and n2, which is x of n minus n1, n minus n2, also has the same Fourier transform. So what's our trick, or how do we get rid of all these problems? Well, first of all, to fix this problem, to fix the e to the j theta problem, if theta is anything but 0, e to the j theta is going to be some sort of a either negative or complex number. Like if theta is 0, it's 1. If theta is pi, it's minus 1. If theta is pi over 2, is j. If theta is 3 pi over 2, is minus j. So it's most of the time it's going to be complex unless theta is 0 or pi. So if I assume my original x is real, signal x of n1 and n2 is real, and in many applications it's not a bad assumption to make, that means e to the j theta can only take on the value theta 0 or theta equals pi. If theta equals pi, then e to the j theta becomes minus 1. Theta equals 0, it becomes 1. So furthermore, so then the ambiguity has been reduced by quite a bit already. Furthermore, if I assume signal is positive, the quantity we're after, the discrete time signal, is also positive, then that forces theta to be 0. It can't even be pi. Okay? So if x is positive, then there is no positive and real, then for sure we can say that theta is equal to 0, and we got rid of problem 1, if you will. How about problem 2, this shift business? Well, that's kind of hard to get rid of, but if we just say we know the region of support of our signal x, we know that it's non-zero between 0 and n, in n1 and 0 and n in the other dimension, then we can get rid of the shift problem. So we're just going to keep adding assumptions until these ambiguities all go away. So now furthermore, assume, so this was to fix the problem 1. Can you roll up, please, so half of the other page is shown? Excuse me, can you roll up so half of the other page is shown? Thank you. So we made assumption 1 to get rid of observation 1, or to fix observation 1. Assumption 2 is that we're going to assume that we know the extent of x of n1 and n2 is known. Okay? That means we're not going to worry whether we know that the non-zero values are in this have this region of support. It's non-zero for n1 and n2 being in this region, and therefore you can't shift it here. And that's not a terribly bad assumption to make either. And finally, for the theorem to hold true, we also have to assume that x of n1 and n2 is irreducible. Okay? Because it's a condition of the theorem. Monty Hayes assumed it. For this equivalence thing to be true, x has to be irreducible, which means that what that means is that the z transform of the signal x is irreducible. And if we assume all these things, it's the real, it's positive, we know its extent, and the z transform is reducible, then we can conclude using Hayes' theorem that we can nail the signal to a factor of 2. In other words, it's either we get x of n1 and n2, or we get its reflection. The reflection one is the one thing you can't get away from, x of n minus n1 comma n minus n2. So both of these things have the same Fourier transform magnitude. So overall, assume the signal is real, x is real, suppose we know, and positive, and suppose we know the region of support, we know the extent of it, then the Fourier transform magnitude can be used to recover either x or its reflection, and reflection is here, uniquely. I use the word uniquely in quotation because it's either this or that. So before I wrap up the lecture, I like to show two things. One of them is some examples of Fourier transform reconstruction, so you can see, reconstruction from Fourier transform magnitude. So after all these mathematics, you can have a feeling that you actually know what it is. So here's a 12 by 12 pixel signal. And can you zoom in, please, as much as you can? So on the left, you have a 12 by 12 signal. Sorry. Here. Zoom out, please. So you have a 24 by 24 signal. This is the IEEE lady. You can tell from her hairstyle that actually there's so few pixels you can't really tell who she is. But if you looked at the high resolution picture, you can tell that this is a hairstyle from the 50s or something, or maybe even 40s, or maybe even 30s. I don't know. And this is the original, and this is the reconstruction using the technique developed by Eennlb and Eennlb. And this is a closed form solution technique. It's not iterative, where he starts tracking the zeros of the z transform in the z domain. And the problem with this is that, at least at the time it was invented, which was mid 80s, you couldn't apply it to any signals that were higher than 24 by 24, or else the problem was the ill-conditionedness of the problem. And just so that you can get a taste of what a reconstruction from, you can also apply iterative techniques to do that. And let me see if I have a flow diagram. I don't have a flow diagram, but you can imagine an iterative technique of the following way, and this is really the last thing for today's lecture. So here's a proposed iterative algorithm to actually practically get the phase or recover the phase from Fourier transform magnitude, right? And for this algorithm, we're assuming that we know the signal at 4n times 4n samples of x of omega 1, omega 2 squared. Just you can be 8n, it could be 2n, whatever, but let's just say we know that 4n. So what do? You start with some sort of initial guess for the signal, and the signal itself has a region of support of n by n, where n1 ranges 0 to n minus 1, and 2 ranges from 0 to n minus 1. We're assuming the x is positive and real. All those assumptions we're going to make, we make. And we're assuming that it's irreducible. And the fact that we're assuming x has a z transform that's irreducible is not a stretch of imagination, because most two-dimensional signals have an associated irreducible polynomial anyway. If you end up having a reducible polynomial, you're extremely unlucky. So the reason this theorem is important is because the condition it requires, the assumption it makes, is easy to make in practice. Most 2D signals have irreducible polynomials. Okay, so you start with an initial guess. Your initial guess is n by n. You compute its DTFT, or you compute its DTFT or its DFT at 4n by 4n samples. And when you go to the computer, no, you can't compute DTFT because it's a continuous variable, but you can compute this 4n by 4n DFT. And how does one compute the 4n by 4n DFT of an n by n signal? Good. Pad it with 0. So now then you take the DFT of it, and now you check out its magnitude. You're given 4n by 4n samples of the magnitude function. You started with some random initial guess, so you ask yourself, are the resulting magnitude the same as what we were given? Is it close? And if it is yes, it's sufficiently close, we're done. Stop. If it is not, what do? Well, we keep the phase that this guy gave us. Remember, when we take the 4n by 4n DFT, it gives us a complex number that has magnitude and phase. We keep the phase that it gave us, and we replace the magnitude by the given guy. So keep the phase, add those 4n by 4n samples, and then replace the magnitude with what was given. And now what do? We take an inverse for 4n by 4n DFT. Inverse DFT, 4n by 4n. So this is all 4n by 4n. This is 4n by 4n. And the output of this is 4n by 4n. And now what do from here? The original sequence we know has a finite extent, and it's n by n. So if I take a inverse Fourier transform, I get 4n by 4n. The remaining 3n by 3n samples have got to be 0. So if this is 0, 4n, 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 we know this is the only non-zero part. This is 0, 0, 0. So you set the extra values in here to 0. So set extra coefficients to 0, because we are after a signal that's 0 here, and it only has non-zero values between 0 and n. Okay? And now you get a signal that's n by n again. And you go back here. You take a 4n by 4n DFT of it, and you keep iterating until you exit out of it, until the Fourier transform magnitude of the resulting signal that you get is close enough to what you were given, in which case you stop. Right? And this algorithm actually, I have personally run it on signals, and I can tell you what you get if you apply this iterative algorithm. If you start with a given image, you get a signal that's a combination of a signal and the rotated version of it. You see both the features of the original and the rotated version in the convert. So this thing doesn't really converge very well. It stagnates, it does all kinds of bad things. And where does it stagnate? It's this ambiguity between the signal and its flipped version that kind of kills you. And one way to prevent that stagnation and that ambiguity is to nail down the signal by adding additional information or additional assumptions. Suppose I know, I don't know, the phase at one point, or suppose I know that I cut a signal in the space domain with a threshold, I know which sample values it's above, which ones is above.